we were considering this problem, and the first thing to do is to figure out what the general solution to the ODE is. So this is an ODE that we're pretty familiar with, second order ODE, and it has solutions. So the second order ODE has solution, general solution. That's x of x, little x of big X of little x, is equal to, there are two cases, right? So we have k1, or k1 and k2 are constants, plus k2 x, which is the case for lambda equal what? This is when there's a double root, right? So this is lambda equals 0. That's when we have a double root here. And then we have k1 e to the j root lambda x plus k2 e to the minus j root lambda x. And this is otherwise, right? So one thing we needed to note here is that certainly lambda is not complex, because it's a Sturm-liouville problem, so our lambdas have to be real. Okay, so that's the first thing to this is one thing that we learned about the Sturm-liouville problem, is that the lambdas are real. So we don't have complex lambdas. They can be negative, 0, or positive, however. So in the case that they're negative or positive, we have this solution. In the case that they are 0, we have this solution. Okay? And this is the general solution. And now we would typically apply our initial conditions, right? But we don't have those. We have boundary conditions. So we need to apply our boundary conditions. So we're going to take first off this case that lambda equals 0, and we're going to see if it can meet our boundary conditions. Okay? So let's try that. So apply the boundary conditions to lambda equals 0. Okay, so the boundary conditions are x of 0 equals 0, so this is big X of 0 equals 0, which implies that, so we have this here, we plug in 0 for x, and we have k1 plus k2 times 0 equals 0, which implies that k1 is what? K1 is 0. Okay? And we have x of L equals 0, which, plugging into that lambda 0 solution, we have k1, which is 0, plus k2 times L equals 0, which implies what? K2 is 0. our solution then, if k1 and k2 are 0, is for lambda equals 0, what is our solution? 0. So this gives the trivial solution, which is that x of x equals 0. Which is just not helpful, right? So it only solves that boundary condition when the solution is just that it's a flat line at 0. So there are no non-trivial solutions when lambda is 0. Okay. Let's take lambda being negative now. So we'll try applying the boundary conditions to lambda less than 0. Okay. If lambda is less than 0, if we look back here, then we're in this row here. Lambda is less than 0. We have the square root of a negative number, which is going to give us a j, right? So to multiply the other j, so then we have e to the j squared absolute value lambda, and then negative j squared. Negative j squared is positive, etc. So we've got, what we can write is our solution is, so x of x equals k1 e to the negative absolute value of lambda plus k2 e to the, oh, there was an x here, right? X square root absolute value of lambda x. So that's our solution in this case. You can rewrite this. You may or may not recognize this identity, but you can use the hyperbolic trigonometric functions here to rewrite this. So it's some new constant, k3, cosh, hyperbolic cosine of absolute square root of the absolute value of lambda x plus k4, another new constant, sinh square root absolute value of lambda x. Okay? So now we can apply the boundary conditions again. So we've got our x of 0 equals 0, which tells us that we've got k3 cosh 0 plus k4 sinh 0 equals 0. And cosh of 0 is 1, sinh of 0 is 0, so this implies k3 plus 0 equals 0, which implies that k3 has to be 0. Okay. And the other boundary, x of L equals 0, implies that k3 cosh square root absolute value of lambda L plus k4 sinh square root turns out that this is only true when L is equal to 0, or K4 is equal to 0. Since is not a periodic function, it goes off to infinity. So we're stuck with K4 equals 0. Now, if sinh could be 0 for positive L, then we would have a non-trivial solution. But once again, we found that K3 and K4 must be 0. So, trivial solution again. Okay. Do we think that lambda positive is going to give us some non-trivial solution? And why? Why do we think? Yeah. So we know that there are going to be an infinite number of solutions, right? Eigenfunctions. It's a Sturm-liouville problem. So we should have confidence that there are some. And there are only 3 possibilities, right? We're not going to consider any other possibility besides lambda being negative, 0, or positive. It has to be one of those. So this has to give us a non-trivial solution. Yeah. But I will mention that in some conditions, lambda negative and lambda equals 0 are potential solutions, non-trivial solutions. In this case, they turn out to be trivial. But in general, when you have other problems, other boundary conditions, you can have a non-trivial situation when lambda is negative. Okay. To lambda positive. So, in this case, we have x of x being equal to, we can rewrite the equation as being k5 cosine square root of, since lambda now is going to be positive, we can just leave it as lambda, and x plus k6 sine root lambda x. And so what we'll do then is we'll plug in our boundary conditions, which are x of 0 equals 0. So we plug that in, we have k5 cosine of 0 plus k6 sine of 0 equals 0. Cosine of 0 is 1, sine 0 is 0, so this tells us that k5 has to be what? 0, right? Okay, never fear. The next one is not going to be 0. So x of L equals 0 gives us that k5 cosine square root lambda L plus k6 sine square root lambda L equals 0. Now this term goes away because k5 is 0, right? But this term, sine of this value of root lambda L can equal 0, right? So what we're left with is k6 sine square root lambda L equals 0. And we need to solve for the values of lambda for which this is true, right? corresponding then for lambda, we get that lambda is equal to n pi over L squared. Sometimes we'll call this lambda sub n for the nth one. Okay? So, what we found are the non-trivial solutions, which are, if we go back to this solution, this is for lambda greater than 0, k5 is going to be 0, so this term will be gone, but we'll have x of x. So we have an eigenfunction, or functions, because there are an infinite number of them. Eigenfunctions, x of x equals sine, we'll call it lambda n, well, I guess square root of lambda n, and it's actually easier to now just plug in n pi over L x little x. And we have corresponding eigenvalues, which are the values of lambda, right? Oops. Lambda sub n equals n pi over L squared. Okay. So I'll post the code for this. Let's see, actually. Oh, yeah, I plot this. I want to plot some different eigenfunctions. So I'll actually pull up the graph because it's kind of a lot easier to see the graph than to do this. So okay. So I just do a little Python, just a little NumPy plot, where I just create lambda n xn, and then I calculated each xn for a bunch of values of x, and I set L equal to 1. And this gives the eigenfunction for n equals 1 is this, which meets our boundary conditions, which is that at 0, the solution is equal to 0, and at L, which we set to 1, the solution is equal to 0. Okay, so all of our eigenfunctions should meet that. And we also want to check this theorem that said that there are going to be n minus 1 zeros on the interval in between. So n minus 1 zeros, so that for the first one there are zero crossings between those 2 points. For n equals 2, we have a full period of a sine wave that happens here. And we get 1 0 crossing, so 2 minus 1 is 1 0 crossing. N equals 3, and we've got the green one, and we get 2 0 crossings. N equals 4, and you get 3 0 crossings. And the boundary conditions are always met. Okay? Now, these things look like modes of a vibrating string, right? Normal modes of a vibrating string, which you guys saw in physics. And that's exactly what this problem is correlated to. So you could look at that. If you looked at a vibrating string, this is one of the parts of your solution for a vibrating string, the PDE. So the boundary conditions are being met. So this is an ODE solution, just like we've always done before. General solution of an ODE. You could do your characteristic equation, solve for the roots of that characteristic equation, sum them up, and it's a homogeneous equation, so we don't have to worry about finding the particular solution. So that was straightforward. The thing that was weird about it was that we had to meet boundary boundary conditions. And we saw how to do that by applying the boundary conditions for different cases of lambda, lambda negative, lambda 0, lambda positive, and finding out what the solution would yield for those different boundary conditions. Okay? I want to be careful here to recognize that there's a distinction here. We're using the same line. We're using eigenvalue here. And eigenvalues showed up in ODE solutions before. And when they showed up before, the eigenvalues were the roots of the characteristic equation. Okay? So characteristic equation, sometimes we've even used lambda to plug in to find those roots of the characteristic equation. And those eigenvalues are finite in number. They're equal to the order of the derivatives in the ODE, right? So if it's a second order equation, you get two roots of your characteristic equation. And those two roots, we've learned, are also the eigenvalues of the A matrix of a state space model that models those same dynamics. So the eigenvalues that we're talking about here are distinct from that, okay? They're not the same eigenvalues. We're not talking about the same eigenvalues. And you can actually think of eigenfunctions as being like eigenvectors. Kind of the idea is that they're the ones that solve the problem, right? They're the special functions that solve this boundary condition problem. So that's kind of it's an important distinction to make between eigenvalues for eigenfunctions and then eigenvalues for the dynamics of the problem, where you've got your A matrix, and you've looked at that as being like the modes of the problem. This is similar, and we'll also call these modes, but they arise by applying the boundary conditions and finding out which functions satisfy those boundary conditions. Okay, so they arise in boundary value problems. All right? Okay. It turns out that this is actually typically the hardest part of solving a PDE problem, is doing the boundary value problem. Okay? So we're most of the way there. We have all the pieces now. Okay, any questions on this? I mean, the plotting stuff is just for fun, to show you guys how it works.
The lambda that we got here will only satisfy the boundary condition and the previous equation you gave us here. Because if we solve using the previous method, we use the general solution.
Yeah, which is essentially what we got. We started with that, right? The general solution gave us the two cases. If you have a repeated root, so it's a second order ODE, right? So it's going to have two roots of the characteristic equation. And if you have that case where they're repeated roots, okay, that's when lambda equals 0, repeated roots, you'll get this solution. And then otherwise, you have this solution here. And so that's comes from finding your two roots of the characteristic equation. If lambda has to be real, then these are the two possible solutions. So that other method was packed into the general solution we wrote here. We've just solved this one so many times that we remember, okay, for a repeated root, this is the solution, and for a non-repeated root, this is the solution. Yeah.
So what we are solving is to find the lambda that satisfies these.
Yeah. So this solution in general does not satisfy the boundary conditions. So this is the general solution of the ODE. Typically, when we have the general solution of the ODE, we would then need to apply the initial condition, right? To find out, like, specifically, this is a family of solutions, right? K1 and K2 can be any number. It solves a differential equation. But to satisfy the boundary conditions, we need some specific requirements on K1 and K2. It turns out that K1 has to be 0 in all cases in lambda, and that K2 can be non-zero if we have lambda greater than 0, and in that case, there are only certain values of lambda that work, right? The eigenvalues are the only ones that work, the lambda n's. So we had to, once we restricted this solution down, we're left with this, which is unique within a scaling factor. You could have done 5 times sine, that would have been okay. Typically, you wouldn't. You would just set the constant equal to 1. But there are different. You guys remember with eigenvectors, it was a similar thing. They're unique within a scaling constant. So, yeah. Okay. So that's boundary value problems. That's the Sturm-liouville